In this lecture, we're going to discuss the basics of memory management. Much of this should be review for you for this class, but it'll be an introduction to garbage collection, which is our next topic. So in all programming languages, you have three types of storage for your variables. There's static storage. This is storage that is allocated and set up at compile time or load time. There is stack storage, which is the runtime stack. This is the user or system stack. I'm going to refer to it as the runtime stack. This is different than the operand stack that we discussed in terms of the Java bytecode language in earlier lectures. The stack in a process that's running, the implementation, the actual execution of a program, holds the local variables and allows functions to be called and returned from over time. The third type of variable storage is heap storage. This is storage that's allocated dynamically while the program is running explicitly by the user. Of these three types of storage, the static storage is primarily used for global storage. Different programming languages do different things with globals, but most languages have a way for variables to be declared outside of any function or class, that is, to be in the outermost scope of the program. And again, just as a review, scope is the set of statements that can access a particular variable. This types of storage, static storage, also dictates the lifetime of these variables, which is, in this case, the start of the program to the end of the program. So as a program is read in from a file and loaded into memory and becomes a process, that is, the CPU and the operating system consider it an executing program and allocate resources to it so it can execute. When that happens, this static storage is allocated as part of the program and it's cleaned up as the program exits. It's good practice, of course, to use globals, this type of storage, globals and static storage, sparingly. If you do use it, you should try to make those variables constant if you can. This storage is segmented in the read-only and the read-write segments of the process virtual address space when a program is loaded into memory for execution. Locals, local variables, these can include parameters and variables that are declared within a function, are stored using the runtime stack. The scope of these variables are the set of statements that are in the function in which the variable is declared, and the lifetime of these variables is from the start of a function invocation to when the function in which they're declared it returns. The runtime stack is also part of the virtual address space of the process as a program executes, and these variables, the storage for these variables, is done implicitly by the runtime. They are allocated on the runtime stack as part of a stack frame when a function is invoked, and it's cleaned up and returned to the system when the function returns. The third type of variable are dynamic variables. Sometimes these are called pointer variables. These are variables that hold addresses, and these addresses come from the heap. The heap is another area of the process's virtual address space. These are variables that hold addresses in the heap that is allocated explicitly by the programmer. Explicit allocation is done with a statement in the language. The most common keywords in the language for explicit allocation of heap variables are new and alloc or malloc. The scope of these variables is completely up to and controlled by the programmer. Wherever the variable is declared, it could be global or local, just like any other non-pointer variable, and that's going to dictate its scope. The lifetime of the storage is from the point of the new or explicit allocation site to when the objects are deallocated. They could be deallocated explicitly with a keyword, something like delete, or they might be deallocated by a garbage collector if the language has that support. On the right in this slide, I have a picture of the virtual address space of a process. This is the layout of a typical process in Linux. This is an example of the ELF, executable and linkable format defined by GNU. At the bottom is address 0. At the top is the high address space. I'm assuming a 32-bit architecture here. In low memory, we have a section that's usually not available for use. Immediately above that, we have the read-only segment. This is where your program code is stored, and any constant global variables also have their storage in this segment. Above that, we have our read-write segment, and this is where all of our global variables that are not constant have their storage. If you're in a language like C, you might be familiar with a local variable with a static keyword. These local variables are unique in that the scope is still the function in which they are declared, but the lifetime of that storage goes beyond multiple calls, goes across calls of the function itself. Any variable marked with static will have the initial default value the first time that function is invoked, but the next time the function is invoked, that variable is going to have the value that it last had at the end of the last time the function is invoked. So the storage and the values are held across function invocations of the same function, but the scope still remains inside the function. Above the read-write segment is the runtime heap. This is where our dynamic variables are going to have their storage allocated from. This is where all variables with explicit allocation are allocated from. So the new command will, in a language, the operation in a language will allocate data from here and return the address that will be stored in the dynamic variable, a variable that holds a pointer's address, or the variable that is a pointer or that holds an address. At the very top of the process address space is part of the kernel that shares the address space with the process. The user program does not have access to this area of memory directly. Below that is the runtime stack. This is where we're going to have all of the storage of local variables and parameters or arguments that are passed between functions. This is a FIFO data structure. It's a LIFO data structure, last in, first out. So we push a stack frame onto the stack each time we invoke a function in a program. When that function invokes another function, we push another stack frame. When that called function returns, we pop that stack frame. And then when the original method that made the call returns, its stack frame will be popped from the stack. The runtime stack in most Linux systems grows from high memory to low memory towards the heap, and the heap grows towards the runtime stack. This is a huge area of memory. If you think about the address space, this range of addresses is a very, very large range of addresses. And somewhere in the middle is typically where the shared libraries are stored that executable programs use. So we're going to focus on heap allocation and deallocation next. Heap allocation is, as I mentioned earlier, explicit allocation, where there is an operation in the language like new or malloc that allocates the storage and starts the lifetime of these variables. Deallocation or deletion can also be explicit. If there's a delete or a free in the language, that is what that's used for, and the programmer can control all of this in certain languages like C++ and C. However, storage and allocation and deallocation can be implicit. This is where the programmers do nothing. For example, local variables. When you declare a local variable, that storage is not allocated. That is just telling the compiler what the scope of a variable is and what its size will be when it actually runs. However, local variables are automatically, implicitly allocated and deallocated when the program runs using the runtime stack frames that I mentioned earlier. Non-heap objects are implicitly allocated and deallocated when they're local and when they're global. Global variables are allocated when the program is given space in memory for execution, and deleted when that space is cleaned up after the program ends. For heap objects, you can have explicit deletion or explicit deallocation, as I mentioned earlier, or for managed languages, that are languages that operate within managed runtime systems, deallocation can be implicit. And when this is the case, that is, when deallocation of heap objects happens automatically, the service in the runtime system that provides this automation is called garbage collection. Garbage collection addresses many of the failures that are associated with explicitly deallocated memory. Problems like memory leaks, where you overwrite an address in a variable and have no way to get to that address. There are no other variables that hold that address. That's called a memory leak. This is where you allocate some memory and you overwrite the addresses so that you can no longer get to them. And that space, it cannot be deleted, it cannot be accessed, so that memory has leaked the system. This can be really bad in systems programs, and it is considered a bug and should be. Dangling pointers are another big failure in explicitly deallocated memory. Really hard for programmers to deal with. This is where you allocate memory and free it in one part of the program, and then use that address after it's been deleted, potentially through another variable, most commonly through other variables. Other problems with explicitly deallocated memory is you may not deallocate it and run out of memory when you really have lots of garbage in the system. Garbage is another way of thinking about garbage is memory leaked data. Any data that cannot be reached by the program anymore because there are no references to it in the program is a leak, and you can just run out of memory if you have leaked lots of memory and haven't cleaned it up. Just memory management in general is just really challenging for programmers to deal with. The errors might occur under certain circumstances, but not in others. They might be time dependent. They may not be repeatable. It's very hard to get these right, and it's really hard to remember when you have complex programs what part of the program is responsible for deallocating memory, and which part is not. When you add multi-threading and multiprocessing, this situation only gets worse, and debugging is so hard that there's entire tool sets and new technologies that have emerged to try to help developers debug their programs, and in particular their memory management problems. Tools like Purify. Garbage collection solves explicit deallocation problems by automating the deallocation process. It tracks every piece of data that the program cannot reach and eventually gets rid of it. This automation requires work at runtime, so there's going to be more complexity introduced into the runtime system as well as overhead. Garbage collection is not the solution to every problem, but it is required for managed languages for which you need, isolation and protection of the host system. So programs that are transferred over the internet that you're executing and you didn't write yourself have to be trustworthy. And because there may be problems or bugs or actual intentional security violations within programs, we require runtime systems that sandbox languages, programs that run to protect the host system. Garbage collection is one mechanism that enables the sandboxing to happen by ensuring that programs don't access arbitrary locations in memory, and that they ensure that their memory is cleaned up when it's no longer being used. Garbage collection, again, is not the solution to every problem, but it does reduce the number of bugs and it increases programmer productivity significantly. However, it has to be thought of as an integral piece of the system and not as an afterthought. And in some cases, it might even improve performance. By the end of this class, you should be able to tell me how garbage collection might improve performance over explicit deallocation by a programmer. Some basic terminology that we start with are as follows. The collector is the memory manager. In some cases, the memory manager runs when you're out of memory, and it goes and tries to reclaim memory for the program. This means that it should not allocate memory, right? It has to be a service in the system that can operate when memory is short or when memory is no longer available to be allocated. The mutator is the user program. It's called the mutator because it can change and allocate memory. It does so through its data structures, manipulation of its data structures. The term stop the world collector defines collectors that stop all mutators in order to perform GC. This is a very simple approach to garbage collection, but also very effective. And it allows the two operations to be kept separate from each other, collection and program execution. This doesn't mean that the garbage collector operates on a single thread. It can operate on lots of threads. Next, we have to reason about the way a program accesses memory if we're going to figure out how to automate the process of collecting memory. So the first thing you need to know is how the program gets to those addresses. Where are variables that hold addresses stored? Variable values can be in registers, physical registers in the CPU, because that's where the operations are going to take place ultimately by the CPU. They can be in the program stack in memory. This is where the function stack frames are located that holds our local variables, holds temporary variables, and so our variables can have addresses on the runtime stack. They can also be in globals in the statics table. If you have watched our earlier lessons in this class, any kind of global segment in memory can hold variables that hold addresses that point to other parts of the address space, in particular the heap where the memory is that our garbage collector is going to clean up. So again, these values that can manipulate memory directly are called the root set of the computation, and they are our processor registers, our program runtime stack, and our global variables, wherever they're stored. These root sets are variables that have references that point to heap locations, and these variables are where we're going to use these variables to find all of the data that our program can access. The data that programs can access are called the live objects, and these are objects that are reachable from the roots. Throughout this presentation and those that follow, I refer to objects interchangeably with nodes and cells. This is data that is allocated in the heap. These objects, this data commonly has headers that we discussed and defined in our earlier lectures from this class. This header typically indicates the type of the object that we can use to understand what the size of the object is. Sometimes objects with headers are also called boxed. This means that they have a header and typically they're stored out in the heap at this point. Uh, the live objects in the heap construct a graph. If you think about all of the roots in the program, the registers, the stack locations, the globals that hold addresses out to the heap, if we follow those addresses out to the heap and we interrogate those objects that are there at those addresses, those objects have fields. Those fields themselves can hold addresses. That is, they can refer to other objects. And so you can build a graph from the roots of a program that identify all of the accessible heap data that the program has access to at a particular program point. Note that this changes as the program executes. Different program points will hold, may represent different live object graphs because the program is mutating, is changing the heap as it executes. Here's just a brief example of how garbage collection works in a managed language. In this case, we're considering Java. We have a static variable, a class variable, so that's going to be a global in our setting, called listLE. Its type is myList. We then start executing a function foo, a method foo. Method foo has a local variable, and the first thing we do is we allocate a new object of type myList, and we store its address in listLE. listLE is, again, a static class variable, and so in our Java virtual machine, it's going to be stored in our global statics table. So this object that we just allocated is reachable from our statics table. Next thing we do is we allocate a new object of type myList, and we store its address in the next pointer of listLE. We repeat this a second time, so now we have 3 objects out in the heap, all reachable from each other. The next thing we do is we create a local variable called localLE, and we have it refer to the address that's stored in listLE.next. Okay, so localLE, because it's a local variable, is stored in the runtime stack frame of method foo. So in that stack frame, there is an entry for localLE. It holds an address, and that address is that of the object that listLE.next is referring to. The next thing we do is we assign listLE null. This breaks the pointer from the statics table to the very first object that we allocated. The next thing we do is we allocate a new object of type object. At this point, we run out of space in our heap, in this example, and we stop our mutators and start our garbage collection cycle. Our garbage collection cycle is going to consider all of our roots. The roots are our statics, our globals table, our stack variables that are in our runtime stack at this moment in time, at this program point, or set of program points if you have multiple threads. There are also values and registers. The values that our program is operating on get copied to registers so that our CPU has direct access to data in its operations. These 3 locations in our programs, the globals or the statics, the runtime stack frames, and the registers consist of our root set. The first abstract phase of garbage collection is detection. This is where we go out and we find all of the live objects in our program. Note, we're not looking for dead objects, we're looking for live objects because those are the ones that we can reach from our program at this moment in time during the execution of our program. We find all of the objects that are reachable from our root sets from our program. From those objects, we look at the fields and we see if any other objects are reachable. In this case, we follow the field next and find that there are other objects that we can reach. The second abstract phase of garbage collection is reclamation. In this case, once we've found all of the objects that are reachable from our program, that is, all of the objects that are live, we can then reclaim the ones that aren't live, those that are dead. So we mark all of the objects that are alive, and then anything that is not marked can be recycled. At that point, we allocate the space for the new object that was when we ran out of memory in our program, and we return the address to that call, and we restart the mutators, and the program proceeds. The first thing we have to do in any garbage collector is detect the data that is live. There are two ways to do that. You can determine liveness indirectly or directly. Indirectly means that we trace from our roots to generate a live graph of our program at a particular program point at which garbage collection occurs. We start with all of our roots and we visit all of the objects that are reachable from those roots. Note that some of those roots will have scalar values in them, the non-object values. We don't chase those. We only follow the roots that have addresses out to the heap, to objects. We go out to each of those objects and see if any of their fields refer to additional objects. And from that, we construct a liveness graph. An alternative way of detecting liveness of objects at a particular program point is to keep a record with each object out in the heap and to store in that record a count. This is called reference counting, and this allows us to determine liveness directly as the program is executing. So what we do, again, in the header of the object, we store a reference count in addition to other things that we've used the header for. But this reference count is a count of the number of references associated with that object at that particular moment in time. We have to keep this count up to date. That means every time we move a reference away, as we reassign a pointer that was once pointing to this object, we need to decrement the reference count. And every time we assign a new reference, a new variable of a pointer type to this object, we increment the reference count. Notice we have to keep this consistent across method calls. If we pass in a variable of a reference type to a function, such that a parameter is now going to alias that object, we have to increment the reference count upon invocation and decrement it upon return from the function call.